Now that we've talked about the correlation that helps us describe the relationship, we've talked about the regression line to help us make predictions. We've also talked about residuals that help us realize how different the observations are from the regression or the prediction line. Now we have one more measurement that we need to include, and that's the coefficient of determination. Sometimes it's called the coefficient of variation, and it's always calculated by squaring your correlation coefficient. So it is literally the correlation coefficient squared. What it does, and this is very important, it explains the proportion of the variability in y. So that's how much the y values are varying around that line. That can be explained by the linear relationship between x and y. We'll often describe r squared as a percentage. So when you get your r and you square it, you'll have a decimal. If you multiply by 100, you can turn that into a percentage. But it's just giving us how well that straight line relationship is able to explain how the y values are changing. The coefficient of determination, while it can be obtained by squaring r, there are some other ways that it's calculated. And if you study additional topics in statistics, you'll often talk about the residual sum of squares and the total sum of squares. The residual sum of squares is just where you've taken each observation and subtracted the prediction, so it's a residual, and you've squared all the residuals and added them all up. And then the total sum of squares, where you take each observation and you subtract the mean, square that, and add all those up. You can calculate that simply by taking the sum of all of the y values squared and subtracting the sum of the y's, then square that number, divide by n. It's still quite complicated. Thankfully, technology does all of this for us. But if you have those values, the coefficient of determination is equal to 1 minus the sum of the squares of the residual divided by the sum of the squares of the total. The implication there, though, is that the sum of the squares of the residuals, if the difference between the prediction value and the actual values are small compared to the total sum of squares, then that proportion is going to be small. Then when you do 1 minus a small number, you're actually going to get a relatively large number. So we can see where those calculations are helping us observe how it is a proportion of the variation in the data. But if you go to StatCrunch and you go to the first screen, you will see the sum of the squares, and it's the error over the total. And so if you take 526.26858, divide that by the total, 773.94816, and then do 1 minus that number, you get 0.32, which is exactly r squared. The last calculation that we will have is the standard deviation about the least squares regression line. We can actually calculate the standard deviation around that line. When we looked at those sum of squares of residual and the sum of squares of total, we saw where the coefficient of determination was measuring the extent of variability about the least squares regression line relative to the overall variability in y. Well, what if there's a lot of overall variability? Well, going back to a previous chapter, the standard deviation is calculated with the formula shown here. It can be interpreted as the typical amount by which a sample observation deviates from that mean. So if we want to find the standard deviation about the least squares regression line, then we'll take the sum of the squares of the residual, which, look back at how that was calculated. It is somewhat similar to how we calculate the standard deviation, and then divide by n minus 2. It's a whole expected value calculus thing, why it's n minus 2. But that value is going to give you the standard deviation, SE. In StatCrunch, you will find that right here where it says estimate of the error standard deviation. That's the value that you are looking for. So you don't ever have to worry about calculating it. It will be provided to you in the output. But what I want you to take away is, even though you're not going to be calculating r squared by hand or the standard deviation or the standard error by hand, what you do need to be able to do is interpret what those values mean. So a small value of that standard deviation indicates that the residuals tend to be pretty small. Small variation, so the residuals won't be very big. That residual is the difference between a predicted y and an observed y. So the standard error can be thought as describing the accuracy you can expect when using the least squared regression line to make predictions. Now, when you have a large value of r squared, that tells you that a large proportion of the variability in y can be explained by that regression line. So that tells you that knowing the value of x is helpful for predicting y. So a small standard deviation tells you that your accuracy will be good. A large r squared tells you that your prediction will be helpful. So together, if you have a small value of SE and a large value for r squared, then your regression line is a good way to make predictions.